The example which we are going to look into now is heat diffusion equation. So we will try to use the finite differencing schemes which we have learnt, like the forward differencing scheme or the central differencing scheme for this particular problem. Before going into the problem itself, let's look at the equation what we have at our hand. So the heat diffusion equation is going to be of the form du by dt, the partial differentiation with respect to time, is equal to, like we had in the case of the advection equation, partial differentiation with respect to x of some quantity which we call d du by dx. As you can see, this is a second order differentiation in space, first order differentiation in time. So that is what we have got in the slide, and this is the equation that talks about the conservation of heat energy inside a control volume, and the change in the energy inside the volume is equal to the flux of the heat that is going and coming out of the control volume. So if we set d equal to constant in this particular equation, we get the second order in space partial differential equation of the form given here. So we will have du by dt is equal to d times d square u by dx square. This is the second order in space and first order in time. So what we are going to do now is we are going to apply for this particular term forward Euler method, that is the forward differencing scheme, and for this particular term we are going to use the central differencing scheme. So that is what we are going to see in the next slide. So we have approximated the partial differential dou u by dou t is equal to un comma j plus 1 minus un comma j divided by delta t plus certain order of truncation which comes from the Taylor series expansion, and we will do the central differencing, as I said, for the second order partial differential with respect to x as follows. Again you will have certain order of truncation with respect to x. So we are using CD only using the terms at time step j, that is more important to know, and if we do that we can approximately equate the partial differential equation to the finite difference equation as follows. So what we have got now is un comma j plus 1 minus un comma j divided by delta t, that is equal to d un plus 1 comma j minus 2 un comma j plus un minus 1 comma j divided by del x square, and as you can see this is the second order partial differential with respect to x which we have used the central differencing scheme, and here we have done the forward differencing scheme. If we rearrange the terms in such a manner that we keep only the u of n comma j plus 1 on the left hand side and bring all other terms on the right hand side and substitute the value r for the constant d delta t divided by del x square, we get this form of an equation. We have seen a similar set of equation while we did the earlier analysis on the finite differencing scheme, and this is the same set of equation, and r is equal to d delta t divided by delta x square. Again this is a forward in time, centered in space, and the stencil for this equation is going to look of this sort. Like in the case of the advection equation, this particular equation is very difficult to model for any real time problem, particularly for the reason which we mentioned before, that the delta t is going to be very small. So we have to go very slow in time stepping in order to make the scheme stable, but this is not interesting because you have to wait for such a long time before anything useful happens. Assume that you are trying to simulate the interaction of a wave that is going and hitting a scatterer. For this propagation you are going to wait for such a long time before it goes and hits the scatterer. So all these things are basically a big bottleneck in simulating any practical problem. So we don't use such a scheme in practical simulations. We will use some other kind of schemes like the staggered scheme or lag scheme, predictor corrector method, so on and so forth, which we will see towards the entire course while discussing other methods as well. There are different time stepping schemes that we will be using to make any numerical method practically usable. Yet another method which will be of interest is the implicit method. We have not discussed about it yet, but I will show some examples while we are discussing for this particular heat diffusion equation. But before going further, let's look into the MATLAB simulation. How does the MATLAB simulation can be done for this particular heat diffusion equation using the forward in time, centered in space? That's going to be our focus. So let's go into the MATLAB simulation now. This is the heat diffusion equation which we were talking about. So we are going to model this using the finite differencing method, forward in time and centered in space. So before going into the simulation itself, let's look into the parameters for the diffusion equation and also the range in space and time. So what we have is we are setting the length of a wire that we are interested in modeling the diffusion of heat on a piece of wire. So what we set is this particular length is going to be equal to 1 unit. So this is the one dimensional x-axis. So we are interested in what is happening in the heat diffusion on this one dimensional wire, and also we are setting the final time, the maximum time that we are going to simulate is also 1 unit. So the parameters we need to solve this heat diffusion equation using explicit method are discussed in this particular part of the code. So we are setting the maximum time step as 2500 time step. We are setting the value of delta t. As I said, this is going to be very small if we are going to use forward in time, centered in space. So that is given by the value t, the maximum time, divided by the maximum time step. So we are going to divide 1 divided by 2500. As you can see, this is very small, and also the number of space steps is going to be 50. So again, the space step is not the one that is going to create the issue here, it's a time step, but again we have to set the space step which we have done here, and based on that we are going to calculate various parameters. So the parameters that we need to solve the equation using the explicit method are discussed here. So the maximum time step is going to be given by max k, which is going to be 2500, and the delta t is the time stepping. As I said, this is going to be very small, so it's going to be 1 divided by 2500, and the maximum space step is going to be 50. This is not going to be an issue here, it's the time step that is going to cause the issue. We need to set the maximum time step and maximum spatial steps, which we have done here, and we see the value of r, which is the stability parameter, which is going to be set as r. The stability parameter which we have discussed in the slide before is going to be 2 times the constant d multiplied by delta t multiplied by dx square. So this is what we have here, and we are initializing the temperature in the wire, and we are putting the boundary conditions. We are going to implement it using the explicit method. Remember, this is nothing but the same equation which we had in the case of the explicit method. So we will go back into the slides and look at this r condition one more time, and also the explicit method algorithm that we have got. So what we see is So the R value is d multiplied by delta t divided by delta x square, that is what we are having here, and we are using the condition for 2 times that value for the reason that there will be the term of 2 that will be on the right hand side, as you can see in this equation. So R multiplied by 2, so this is the value that is going to be the most critical value, that is why we are making the value that is 2R, not R itself. So let me explain this using the stencil one more time. So what we have now is stencils. So if we say this is j, this is j minus 1, this is j plus 1, and this is n, n plus 1, n minus 1. So we are interested in computing the value at this point, which is going to be n comma j plus 1, and we are going to use the values that are in n plus 1 comma j. So n plus 1 comma j, this value, we are going to use the value at n comma j, and we are going to use the value n minus 1 comma j. So these are all going to contribute to the value of the solution that we are going to compute here. Interestingly, the time needed for the solution to propagate from this point to this point is going to be shorter compared to the point here to here, the time that one solution needs from here to here. So the solution dependence at this point is going to be more critical for the stability rather than the solution propagation from this point or this point. That is why we are going to take the coefficient that we have in the equation for u of n comma j. So this is n comma j. So we are going to take the influence of the point n comma j more significantly than the other point. So that is why we are setting the condition that twice d delta t divided by delta x square should be less than or equal to 1, and that is what we have set in this particular equation. So the reason why we have set it for R as 2 times d multiplied by delta t dx square is for that reason. So maybe it might be helpful if we change this one into b and explain this in the comment so that you do not get confused. So we will keep this one as b and explain this in the comment. The stability condition depends on solution propagating from the point n comma j, hence we use b equal to 2 times r. So that is why the reason we have 2 here. Other than that, we can change this one back to b here because we have changed on the top the simulation parameter as b. So this is a stability parameter, so it should be clear now that we are using twice because the stability condition is going to depend, maybe we can write it as stability condition depends more on the solution propagating from the point n comma j, hence we use b equal to 2r for the stability parameter. So the code should be self-explanatory for you to run it and test it later on. So with this background, so we are going to simulate this particular problem and see what is going to happen. Later on we can manually set the value of b at different limit and see what is happening. For now, let's run the code. So we are running the code now, and we are going to see what's going to happen. So what we are plotting here is we are plotting the value of the temperature at different selected times. We are plotting at time step 1, time step 100, time step 300, time step 600, so on and so forth, using different colors. So what we see is exactly that, and then we are also plotting in the 2D mesh temperature within, we can write temperature using explicit method, and we are seeing the time step and also we are plotting the temperature. So with that we can interpret the result now. So what we see as result, let us run it one more time, heat diffusion equation. So temperature using the explicit method. So what you are seeing are the two graphs. So the first curve is the initial temperature at different time step, and then you see that it's changing over a period of time. And also we have to see what is the value of B we are using. If you see, we are using B equal to 0.5, but if we try to change the value of B, let's say we are going closer and closer to 1, let's see what's going to happen. So for doing that, what I'm going to do is I'm going to comment this particular part of the B and manually substitute the value of B. So I will save this one. So I am going to set the value B equal to 0.5 once again, and I am going to simulate this equation, and I am getting the same result, which is good. Now I am going to change the value of B to, let's say, 0.75, and now I am going to simulate the same equation, and I am seeing pretty much the same result. So now I am going to change B value to 1, and now I am going to simulate the same result, and I will start to see the value is still okay, but the moment I go more than B equal to 1, let's see what happens. So we are going B equal to 1.1. You start to see some kind of error, which is, you see that it's going to 1 into 10 power 30, which is a clear case for instability. So maybe we can try to go B very, very low. So I'm going to change the value. Now I'm going to run the same equation. It's still okay, but if I go 1/100th the point more than the accepted value, it's still okay. So 1/10th more than the expected value. Now I start to see the instability coming into play. The solution still looks okay, but the instability is already starting. So what we have done now is to show that we cannot go more than the maximum limit by an order of more than 10. So if I start going at 0.1, this will not be useful at all. You will see that the instability is clearly there, and the value is 1 into 10 power 30. So even by going 10% more than the allowed value of the maximum simulation time stepping, it's already not working. So as I said, this is a classical example to know how to program the finite differencing scheme using forward in time and centered in space for heat diffusion equation. We'll provide you this code for you to try and practice a little bit the simulation as well, and this is also a good way to learn certain criteria that one has to know while modeling, like the initial condition, boundary condition, so on and so forth, which will enable you to do advanced coding later on. So I encourage you to take this code and practice it and get a sense of it. we solved the heat diffusion equation using the explicit method. So I would like to recap on the explicit method what we have done, but what we are going to do now is we are going to do it using implicit method. So I said we are not going to go into detail about implicit method as much as we will do for the explicit method. I said explicit methods are much more easy to do numerically, whereas implicit method you have to do a lot of matrix inversion and condition the matrix, so on and so forth. So for our kind of problems it's not something that I would encourage you, although some kind of problems might be easy to solve using implicit methods. So that will not be our main focus area. But that being said, I don't want to leave out on the implicit method altogether. So we will look into the implicit method briefly in this particular part of the lecture. So we will recap on the explicit method which we started with, and then we will take you to the implicit formulation of that particular problem. So remember, we started with the explicit method for a heat diffusion equation which was given by this particular form. So we had the forward in Euler and centered in time for this particular heat diffusion equation, and we did the explicit formulation in such a manner that we set the value of R, which is going to be the stability criterion factor. We also said it's going to be twice this value that is going to be of interest for us because we have a 2R value, and I also explained why we have to take 2 times the R value as the maximum limit for the stability criterion. This explicit method, as we saw in the previous case, is going to have the disadvantage of going very slow in time stepping. So we will try to solve this problem by going to the implicit method. Before going into the implicit method, I would like to start with the basic formulation itself. So the basic formulation is we have time stepping, which is du by dt, that's equal to d t square u by dx square. We said d is going to be a constant, so we are taking out of this equation and we had this form. In the implicit method, what we are going to do is we are going to do forward in time stepping like the way we did for the explicit method. So we are going to do u of n comma j plus 1 minus u of n comma j divided by delta t is equal to d u of n plus 1 comma j plus 1 minus 2 u n comma j plus 1 and plus u of n minus 1 comma j plus 1. It's going to be the numerator and we are going to divide it by delta x square. So the stencil of this is going to look very different to what we had in the case of forward Euler method. So remember, so this is our stencil. So we are in j minus 1, j and j plus 1. So we are in n, n minus 1 and n plus 1. So for such a problem, what we are going to have is a stencil. We are interested in computing the value at n comma j plus 1, but we are also going to take the value at n minus 1 and n plus 1 comma j plus 1. So here is the n minus 1 comma j plus 1 and n plus 1 comma j plus 1, and we are going to use the value at n comma j, so which is the value here. So this is the value that we know, and we are interested in computing the value at n comma j plus 1, but obviously we don't know these other two values as well because these are also at time step j plus 1. How are we going to do that is the method of implicit calculation. So what we are going to have is a set of simultaneous linear equation at each of the time step. That being said, fortunately for this kind of problems, it's not going to be very difficult because we can lump those elements in a clever way. We can get a nice tridiagonal matrix. So let's look once more how the equation is going to be in the case of implicit formulation. As I said, for this particular problem, you have to write the equation in the form where you know the value at u of n comma j, whereas you don't know the values that are other than u of n comma j. You don't know this value, you don't know this value, you don't know this value, and you don't know this value. These are all the values that you are going to use and compute. As we can see, you have u of n comma j plus 1 on the left hand side and also on the right hand side. That is why it is called as implicit method. And like in the case of the forward in time, centered in space, as I explained just now, we will do the same thing for the time derivative, except on the right hand side we are evaluating the values at time step j plus 1. So the scheme is going to have a stencil like this, as I have explained before. The value at black dot is the value that we know, whereas the other points we don't know. And let us go and look at the MATLAB simulation for this particular problem, and I will explain you the code and how the matrix inversion is going to look like. So this is the MATLAB simulation for the one dimensional wire problem that we have previously solved using the explicit method. Remember, in the case of the explicit method we had this strong condition on the B. We are going to now see in the implicit method we don't have that strong condition. So what we will start with is the same problem with the time step exactly the same as before, whereas here the parameter B is going to be a little bit more relaxed. Remember that in the case of explicit method we said that the stability parameter is going to be a hard condition, we can't go beyond 1, and obviously when you go beyond 1 you end up into instability issue. We will see in the case of implicit method we don't have such a hard condition. So we will start with the same problem. We have set pretty much everything the same way, except for the case of B we are not going to take twice the value, but we are going to take the value as directly d multiplied by delta t divided by dx square. So you compared to the previous case where B value was 2 times that value, here it is set as this value, but again this is not going to be a hard condition, we can go a little bit beyond the limit as well, and you will also see that the scheme is quite stable. In fact it is unconditionally stable, so that is what the good aspect about implicit method. But obviously as I mentioned it is going to have the problem of matrix inversion. So you will see that we are doing the matrix inversion here. We have lumped these matrices as per the equation what we have. As you can see, this is the minus B value which is corresponding to the minus R in the equation what we have here. As you can see in the slide here you have the value of minus R, and this is represented as B in the code here, and the other values are 1 plus 2 times R is this value what you have here, that is something that you have here as well, and then the third value is the minus R value which is the minus B value here in the code. I have kept it as minus B because in the explicit formulation we also use it as minus B, and but you can make the comparison easier here. What we have done is we have lumped those elements in a clever way, and then we are doing the matrix inversion accordingly, and this way we are able to solve the problem for any B value. So what we will do now is we will run the code now and see the value of the output of the temperature. So this is the temperature and this is the value of the temperature across the one dimensional wire, and we see that for different time steps. So what we can do now is we can see how much influence that the B has on our code itself. So we can write the value of B. B is now 0.25, and I am going to change the value of B to certain other value. Let us say I am going to put B equal to 0.5, and I am going to run the same program, heat diffusion implicit, and you see that it still gives the good result. So let us now go and do the value for B equal to, let us say, 1.5. Now we are going beyond the CFL limit, and we will see how the code works. This code works really good. Remember that we were not able to go beyond 1.1 in the case of explicit method. So we see that it is working pretty fine. We can try to even go beyond that. We will put 2.5 and we will run the code. You will see that it still works fine, and in fact you will be seeing that it works fine for any amount of b, but obviously it has to have a finite b value, so that we are keeping it in such a way that we get the required result. So what we have demonstrated in this particular code is the efficacy of using implicit method. So we said that implicit method is not going to be bounded by the CFL limit. The only thing is we have to do the matrix inversion, and in this particular problem it's easy to do because we can get a tridiagonal matrix and we are able to do the matrix inversion easily. But when the size of the matrix becomes bigger, it becomes cumbersome to use implicit methods. So you have to make an informed choice on what kind of method you are going to use, but it's enough to showcase the value of an implicit method for the problem that we have in our hand. We can easily compare the result with the explicit method, and I encourage you to use the code to also test the same way you did for the explicit method, and try to learn a thing or two about the implicit formulation, and practice simulation as and when possible, so that you are comfortable using the method for various other problems. Thank you.